Okay, so our next presentation is going to be from Professor D.K. Panda from Ohio State University. And this is just one of 3 presentations that he's going to be giving during the workshop. The first one's really going to be related to MPI, an overview and some optimizations. And tomorrow he's going to be more talking about advanced features and essentially what's next. So, D.K. Panda.
Okay, thank you. Good morning. How are you people doing? Okay, so Professor Snake's talk is a very good motivation for this one. Okay, as he talked about all these applications. Okay, so think of all these large clusters are coming up, and we want to get the best performance on these clusters. Okay, to understand the scenarios throughout today's talk and tomorrow's talk, think of like MPI, or which is like MPI library, is like a car. Okay, so people drive the car. Cars are designed, and cars has a lot of features. But when the car comes out of a factory line, it has some default settings. Okay, but it is driven by all people in the world at all different places. So the same exact settings may not work for all the people. Okay, as an user or like a application writer, you need to, when you are running your applications, you just need to tune a lot of things. Just like you are trying to tune on your application, you also need to tune a little bit in the MPI library. Okay, so that just like you are driving, let's say you are driving on the hill or driving down or driving in a desert, driving in a rainy season, you need to make some adjustments in your driving. The same things we can do with the MPI library, and that will lead you to the great performance. And that's what I'll be talking today. I'll also be talking tomorrow. So before I start, I'm sure all of you know about MPI. Is there anybody in the room who doesn't know what MPI is? Okay. How many of you have used MPI? Okay. Some. How many of you have looked at MPI results and analyzed those? Okay, some of you. How many of you have designed MPI libraries? Okay, some. Okay, so that's what I'll be talking here, and you will be seeing how to take things from the lower level to the upper level. Okay, so what I'll be talking today, just to give you a very trends in the designing the petaflop and hexaflop systems, overview of the programming models and MPI, just to give you like a quick primer if you are not familiar with what MPI is, and then little bit go into the MPI features and how to use these. So this is just like the cars, like the different kinds of features come. So I'll be talking about the common features which the MPI library users actually use those. And then I'll go into the overview of the MVAPIS to MPI stack, which we have been working at the Ohio State for almost last 12 years since the beginning of InfiniBand. And I'll go into a lot of these knobs and features there and indicate how it actually interacts with multi-core platforms, with different kinds of networks, different kinds of features of these networks, and how you need to tune it to get the best performance in all these platforms. And go into a lot of these detailed optimization and tuning techniques. So many of you might have seen this chart. This is like from the top 500, it shows like how the field is moving, and this is the line which is trying to show how the top systems have been going up. So just last year we crossed like this 8 petaflop of the K supercomputer, and people are predicting like 20 to 30 petaflops in the 2013, which is not very far away, and we'll be seeing some great machines are being built, and then around 100 petaflops in 2016. And finally, people are looking at the exaflop systems in the 2019 and 2020. Okay. So when we are talking about all these systems, over the years, there have been a lot of great progress, especially in the field of clusters. Okay. So here if you see, this is a chart taken from the top 500 in the November 1996, only 0 systems were of clusters. So that means these were all the traditional IBM, Cray, those kind of machines were there, and gradually clusters started coming in June 1997, only 1 out of 500, And then over the years, if you see, the last several years, we are hovering in the 80 to 84%. Okay? So commodity clusters with commodity interconnects are trying to deliver very great performance for all these applications and taking a lot of higher positions in the top 500 list. And out of those, of course, the InfiniBand is getting a lot of momentum, as many of you might be knowing. So this is from the November 11 top 500 list. There are 209 IB clusters, and these clusters are coming, like a lot of these clusters are of even crossed 100,000 cores. And the next round of systems, you'll be seeing like 200,000 cores, 400,000, 500,000 cores will be coming up. So the question is like, how do we design these kind of systems, and what kind of programming models do we use? Okay, because these are like the clusters, you just put a lot of multi-core platforms together with InfiniBand or let's say some GPU accelerators, but you need to program. Okay, and that's what we'll be talking now. And by the way, please feel free to interact. I mean, so we'd like to make it more interactive. So if you have any questions, just raise the hand, and we'll try to go into more discussion. So most of you know, like the parallel system, the focus is that we need to get greater compute power compared to a serial system. Okay, so if we put together, like let's say 100,000 cores, we expect to get 100,000 speed up. Okay, compared to running it on a single core, but most of the time we don't get. Okay, but the ideal thing is that if we can get the speed up exactly as the number of processors, then we'll be good. You can't do anything better than that. But in order to do that, the fundamental thing lies is that you need to do the complete overlap of computation with communication. Okay, so for example, if a parallel application is trying to do some communication and you are trying to also do some computation. Now if we can overlap, so all the communication cost will be zero, then you can keep the machines busy all the time, and then you will get the perfect speed up. But that doesn't happen. Everybody is trying to go towards that goal. And also, like, we try to handle the problems that are too big to fit in one computer. So then different types of systems have been designed in the past. Like traditional ones, very old systems used to be uniform shared memory systems or bus based. So that means from each processor we get the memory as a uniform manner. And then the non-uniform shared memory or NUMA systems came. So this could be the entire machine, or it could be like one of the nodes. So these days, if you take like AMD Magni cores or Intel Westmere or Sandy Bridge, all the systems are non-uniform memory access. And I'll go into more details on that. And then, of course, we have distributed memory machines. So that means we have machines, each node has its own memory, and then we are trying to connect all these things these are the commodity clusters or Blue Gene or Cray XT5. So these are the kind of very basic principles of how the processor is interacting with the memory. So to run programs on these machines, we have different types of programming models, shared memory or distributed memory. And this slide illustrates that concept. So here it is, the pure shared memory. So that means all the processors are seeing the memory in a uniform manner. So anybody can do read and write. Okay? So that you can do these days within a node, but not across the nodes. And if you want to do it across the nodes, you of course need some kind of additional library support. There are a lot of products out there which can also try to give you that, but it doesn't scale to very large scale system. The common one is the distributed memory model. So that means each processor has its own memory, and we are putting our data here, and they are just communicating over some network. And this is where the MPI comes, which is the message passing standard, and we use that to exchange data and do the communication across the nodes. And the next one which is coming up, which is known as partition global address space, it is like a logical shared memory. So even though physically they are separated, we somehow abstract it in a logical manner to the programmer so that the programmer can actually do read and write. Okay, so there are a lot of newer models are coming up like global arrays, UPC, Chapel, X10, SMEM, CAF, a lot of those. And these are the things I'll be talking tomorrow, and we'll see how the MPI can be combined with these kind of programming models, which are coming to known as hybrid programming models. And people call it like MPI plus X, and X can be any one of these, nobody knows. And that is the kind of thrust for the exascale systems. So with that kind of thing, so let's say this is like the MPI we want to focus on. So how do we really design it? Again, as I said, like think of like MPI library as a car. Okay, so just like we see, car has engines, car has tires, car has all kinds of doors, mirrors, all these components. The same thing happens. On a cluster, so we have processors, we have networks, tomorrow GPU or the Intel mic, all these different components are coming, and we are trying to put this together to build the cluster. So here it is a small animation which will show you, like let's say here we have commodity computing architectures, multi-core, many-core, accelerators all are coming. Then here we have different kinds of networking technologies, whether it is an InfiniBand or 1040 gigi or intelligent NICs. So these are like some fundamental components we want to put together. Now from the top level, these are the like applications or libraries, like the previous talk we heard. So a lot of these applications are there. It could be stencil code, it could be some specific types of code or libraries. And this is where we want to get the best performance. Okay? So think of like the car example. It is like the Formula racing car. Okay? There are drivers, there are cars with all these components, and you want to get the best performance. Okay? So we want to deliver the performance at these levels. So what it means that these applications are written with some programming models. Okay? And I talked to some of these earlier in the earlier slide, like there is a message passing interface, or it could be simple sockets. This one we'll see a lot of things on the third day of the talk. A lot of enterprise applications are still written with sockets. So the question is, how do you deliver performance to those sockets kind of applications? Or it could be these PGAS, which are like UPC or global arrays. So what it means here that to deliver performance at this layer, we need to deliver performance to this layer. Okay, and then to breeze from these programming models to these underlying components, we need to write this library or runtime. And this library or runtime has all these components which actually matches very closely with the lower level components. So that means we need to handle point-to-point communication, collective communication, synchronization logs, I/O file system, quality of service, fault tolerance, etc. Okay, and this is what I'll be going into more details in the later slides. Okay, so just to any questions so far? Everybody is in sync? Everybody is awake? Good. Okay. So now let's take a very quick history of MPI. Now prior to 1994, if some of you are old enough in this room, you will see that that time what used to happen is the late 80s kind of things. Every time a new parallel machines used to come, people used to write their own library there. Okay, each vendor used to push there. At that time it was the old Cray, SGI, Intel, the IPSC. They had some like supercomputers, if some of you remember IPSC-1, IPSC-2. So every time they used to write like roll out a machine, they had their own libraries, own communication libraries. And in one way, they were trying to protect their products, but it used to put a lot of pressure on the application writers, because let's say you are an application writer, you have tuned your machine or tuned your application for a machine X. Tomorrow you buy a machine Y, you need to totally rewrite, and that was a big pain. And gradually all these machines became heterogeneous, and your application cannot run on all these machines. And this is where the community started thinking that, can we have some kind of a standard so that we can decouple the application, the parallel application writing, from the underlying machines. Okay, so there the goal was to come up with a portable, efficient and flexible standard for writing parallel applications, and it can be the application can be written with C, C++ or Fortran. It is actually not an IEEE or ISO standard, but it's widely considered as like an industry standard for HPC applications. And this is where the first standard MPI-1 came in the 1994, and after that, like almost a few years later, then people tried to find out that, okay, we'll try to introduce some newer primitives so that people can even easily try to write the application. So this is where MPI-2 came. And for almost like 12 years, the MPI-1 and MPI-2 have been the most common standards. And then starting from 2008, the MPI 3 effort has been going on. And again, I'll be talking more about that tomorrow. So what does MPI means? Okay, so here there are like primarily as we discussed earlier, let's say there are two processors, P1 and P2. They have their own memory, some data, and they are connected with a network. Okay, and as we know, since it is a distributed memory machines, these processors need to talk to each other or exchange data to proceed with the parallel computation. So MPI 1, for example, here if we see, let's say it can do like a send operation called MPI send to send some data from here to there. Or let's say if you have an MPI 2, which introduced one-sided operations, you can do a get operation. So that means this processor can initiate a get to get data from the other processor's memory. Or you can think of like some collective operations, like here it is an example of all reduce. So that means we can take every processor has its own data, and using some primitives, we want to actually take all the data and perform some reduction operation, let's say with a sum. Okay, so this also leads to multi-way communication. So this is like a very high-level perspective of what MPI does, and then I'll try to go into more and more details. So if you think of like within MPI, these are like the broad features, and this is what I was telling, like in the car, so there are some basic features. I mean, you have an accelerator, you have some gears, those kind of stuff which commonly we use. So this is what happens here in the MPI. So that means point-to-point, two-sided communication, collective communication, one-sided communication, job startup, and parallel I/O. So I'll just be focusing on these 5 stuff. So the point-to-point communication, again, it has a lot of different varieties. So depending on how you want to use these things with respect to your applications, you can get different kinds of overlap. If you remember, I mentioned like we want to really get the overlap between computation and communication. So here there is a synchronous MPI S send. So what it does is the sender process blocks on send until receiver arrives. Okay, because we are talking about a parallel program, we cannot guarantee that they are all going in a synchronous manner. Okay, so if I am sending something, we might try to wait until the receiver actually comes to that point. This is the synchronous send. The second kind of primitives are called blocking send or receive, like MPI send, MPI receive. These are the most commonly used ones. So what it says is like a block until send buffer can be reused. So that means I am trying to send something using a buffer, and after some time, if I want to send, I just wait until that data goes out. Okay. So the block until the receive buffer is ready to read, that is the MPI receives. Now these days with the modern networks, what is happening is like especially InfiniBand or IORP or any of these, the Rocky, those kind of platforms you see, we have RDMA. So there is a decoupling kind of things from how we initiate the operations to what happens over the network. Okay, and this is where actually a lot of non-blocking features can help you. Okay, in the sense, instead of blocking, what you can say is like MPI I send or MPI I receives. So these are like non-blocking operations, and it starts the send and receive, but don't wait until the operations to be complete. Okay, so you just say MPI I send, and the MPI library internally is talking with the network and then trying to send the data out. Okay, and then the processor is not waiting, and it moves ahead with the computation, and then later on it actually comes and checks whether the data has been sent or not. And this actually allows you to do good overlap between computation and communication. And there are other varieties like buffer send, send receive, ready send kind of things. They are not used very frequently because it's a standard. When the people proposed the standard, they actually introduced all kinds of primitives, giving a lot of flexibility to the end users. And over the period of time, some of them have become very common, whereas others have not been used that much. Now, the other aspect of any MPI library is called message matching, okay, or sometimes called tag matching. There are different terminologies which float around. So the idea is that if a lot of people are sending data to me, how do I know that which has come from where? Okay, because in any parallel application, a lot of processes are communicating with each other. So how do we know that which send is for which receive? So this is where actually the programmer, that is you, need to provide this information. When you are writing the parallel application using MPI, the sender side has actually tag, destination rank, and communicator. Okay, And the communicator is actually a subset of the entire set of MPI processes. In the MPI term, there is something called MPI COM world, which represents everybody in that MPI process. And from that COM world, you can create different kinds of subsets depending on how you are trying to talk to each other. And the receiver side, exactly again, we say tag, source rank, and communicator. So the broad idea is that every time I have a receive and somebody has done a send, I need to actually match that these three things match: the tag, the rank, and communicator, to make sure that I'm getting the actual message. Of course, to give some flexibility, there are some other features like MPI any tag, MPI any rank. Depending on your operation, let's say I'm trying to do a barrier, it doesn't matter from where I get it. So in that case, I can say MPI any tag or MPI any rank kind of stuff. Okay. Now there is also the one common thing within the MPI library is the buffering. Okay, so that means, as I mentioned earlier, like different processes can go in its own speed. So sometimes there is a lot of messages can come. Now within the MPI library, there are some ways to buffer this for some time. Okay, and so it is pictorially trying to say like application is sent, that might have gone here, but the receiver might not have posted the receive. The receiver is still trying to do some computation. So what we want to do is trying to actually buffer it inside. And this is to optimize throughput. That means do not wait for the receiver. But this is opaque to programmer. So the programmer doesn't know that. So this is happening within the MPI library to make sure that the different processes can move at the fastest speed. But of course, there is a finite resource, that buffering, because we are taking some amount of memory to provide this buffering. We can guarantee, let's say, to hold up to 100 messages or 200 messages depending on the library. But beyond that, the senders need to be blocked. Okay. So the blocking send, which I introduced earlier, may copy to sender system buffer and then return. Okay, and then the library can try to send the data after that. Now this again, like the big thing, especially for application writer, the blocking versus non-blocking. As I mentioned, blocking send returns when it is safe to reuse the buffer. Okay, maybe in the system buffer, and receive only returns when the data is fully received. But on the other hand, the non-blocking returns immediately. That means data may or may not be buffered. So if you are doing MPI send, you can immediately return. That's what the MPI semantic says. But internally, whether it is buffered or is being sent in some manner, it doesn't care. It simply requests the MPI library to transfer the data, and it needs to wait on the handle returned by the call. And as I mentioned, you can do an isend and keep on computing. And then later on, if you want to again send or reuse that buffer, you need to check with the MPI library to see whether that data has been sent or not. Okay. Now, over the last several years, we are actually interacting with a lot of application folks. And I'll give some examples later on. Like in the previous talk, we heard about this AWP ODC, which got the Gordon Bell finalist in 2010. We actually worked with them. I'll show you those very detailed numbers. And the way we see that, always like the application writers always lag behind. Okay, I mean the technology moves ahead, MPI library comes back, and then the application writer gradually tries to catch up. So if you're an application writer, you need to pay an attention to these kind of newer primitives, how they are being designed, okay, so that you can actually rewrite your applications and get the best performance. And what we've seen is that a lot of applications are still using these blocking operations. And if you can change those to blocking to non-blocking, you'll see you'll get a very good overlap and speed up. Okay, but many people still don't know all those tricks. Because if you don't do, you cannot just change blocking to non-blocking or send to isend, because there will be some data corruption and all those things will happen. So you need to make sure that the semantics you are preserving, but that will allow you to get very good performance. Okay. So now let's go into collective communication. So the collective communication, again, it is kind of used for synchronization, or it's a barrier. So that means, let's say different processors are moving ahead. At some time, we want to make sure that they are synchronized before we go into the next step. Or we can do it for data movement, like a broadcast, scatter, all-to-all kind of stuff. Or it can be used for like collective computation, like all reduce. Let's say you have, every process has some data, and you want to all reduce it to some max, mean, sum. So here again, the same operations, like same considerations come in, like a blocking versus non-blocking, just like what you are doing for point-to-point. Of course, so far, in the MPI standard, all collectives are blocking. Okay, so in fact, that is actually a big bottleneck when we are trying to scale these systems to very large scale. Because let's say you are trying to do a broadcast or an all-to-all, it will take a lot of time, especially let's say on 100,000 core or 200,000 core. And if we do it in a blocking manner, till that time the processors are idle; they are not doing anything. Okay, and that actually, if you think of like the basic Amdahl's law, most of you know, like in the computer science, if that becomes like your sequential portion, then your overall speed up is limited. So that's why in the MPI 3, people are trying to move that into non-blocking versions, and I'll talk about that tomorrow. And we have done a lot of work. MPI 3 has done their first reading of the non-blocking collectives, and especially with InfiniBand, like the core direct support in the ConnectX 3, ConnectX 2 onward, you can really also overlap using non-blocking collectives, because the hardware will try to do those operations, and then you can really overlap your computation, and then you can get very good performance and speed up. So I'll talk more about that tomorrow. Okay. So here it talks about a very small example of like collective operation. Let's say this rank 0. There are 4 processes, and the rank 0 has this data to distribute. So this is like a scatter. So you want to send this data here. There's an array here, array here, array here. So of course you can do it with point-to-point operation. Okay, but you need to take the data, pack it, and then send it. Otherwise, what you can do is just to facilitate this operation, MPI standard has this collective operation called scatter, and then once you do saying MPI scatter and give a pointer to this array, then the underlying the scatter within the MPI library is able to do these operations. So that becomes much more easier for you from a programmability point of view. It makes the job of a programmer much easier. Now the point-to-point and the collective, so these were a part of the MPI 1 standard, and then the MPI 2 standard especially introduced something called one-sided communication. Okay, and the idea here is that when you say send receive, so that means I am sending, you are receiving, so this we call like a two-sided. Okay, but the one-sided is basically saying it decouples the data transfer with synchronization, and especially it is good for irregular pattern of communication. Okay, because even though send receive, I send, unless you are ready or in your computation you don't reach that point, you will not be able to receive the data. On the other hand, one-sided allows me to, let's say, do get operation from you, or I can put some data to you while you are doing the computation. So it allows for better overlap of computation with communication. And the way it works, there is a typically like you can take some memory from every rank and then create some window, and each process can contribute part of memory to form a larger window of global memory through collective operation, and after that you can do get and put operations. And there are a lot of different semantics here in the MPI 2 one-sided. So broad thing is put, get, or accumulate, that is the communication, but it also is associated with some synchronization, because now different processes are interacting with each other, so we need to make sure that if somebody is writing to my memory, how should I be taking it? Okay, so there are some different ways to do active versus passive. So that means active means both the processor or the group of processors participate in that synchronization. Okay, and here we have some, either you can do through fence or you can do through post wait start complete, or the newer model is called passive. So that means we can, while you are doing the computation, I can do a lock or unlock. Okay, so I can send some data to you, or anybody can send the data to you, but each one of them have to do a lock, send the data, unlock. Then the next person can come again, lock, write, and unlock. Okay, and especially with the modern networks, let's say example of InfiniBand, it has the RDMA operation, it has the atomic operations. So all these things become very nicer. You can implement this with a very low overhead on all these modern networks, and that too we have done a lot of work, a lot of research on those, and all those things are in the MapIS2 stack, and I'll be talking some of those later. And this is actually also that AWP ODC example the previous speaker talked. We actually used a lot of these techniques to speed up that application. Okay. Now the other aspect which a lot of people ignore is called job startup. Okay, and Of course, this is like a little bit different, but it is also a part of the MPI, because when we are talking about like 100,000 cores, you start the job, many times that becomes itself a bottleneck. Okay, in fact, it's almost like 4 years, not 4 years, like I think 7 years back, when multi-core platforms were coming. The previous to that, the job startup was based on each process. Okay, and when like the TAC Ranger, let's say, which many of you might be knowing, like a 64,000 cores, that was one of the very largest system which was deployed. So there itself, like sometimes the MPI library was taking several minutes, 9 minutes or 10 minutes to start a job. Okay, and that is clearly not acceptable. So there we actually worked with them, came up with a better way to do it, to reduce to even to 1 minute or even less than 1 minute. Okay, so a lot of work is taking place here. So this MPI is like a process managers to provide support to launch jobs, and typically MPI exec is the utility to launch the jobs. So you can use like MPI exec to process machine file a.out, and of course MPI supports SPMD as well as MPMD, multiple program, multiple data. And there are also different resource managers like Slurm, PBS, Torque, many of you might be knowing. In our MVAP is to stack. This is what we did the design, MPI on RSH 7 years back, saying it was a newer kind of paradigm which we put so that we reduce the startup significantly. And after that, all other MPI stack are using very similar kind of mechanism, either it's a Hydra or OT. So the broad idea is that the launch time should not increase with the number of processes. Okay, otherwise what is happening is like you are eating out time, and then you don't get the overall speed up. So you need to make sure that your job startup is also very done efficiently. And final thing is parallel I/O. And parallel I/O is of course important for many scientific applications, because now especially we are talking about data intensive, and we are moving into like already in the petabytes range, people are talking about exabytes range. So not only we do computations, we also need to get the data in and out. And of course there are parallel file systems like PBFS, Lustre, GPFS. They allow the high bandwidth data access to the large volume data. But then the MPI applications typically use the MPI I/O layer. Okay, and these are the primitives to handle the I/O, and there is a concept of collective I/O, and this actually helps to do these operations efficiently. Here is an example. So let's say the MPI processes might be trying to initiate some small individual request, but then the collective I/O framework actually helps to combine some of these things into bigger chunks, and then finally you try to write it to a file system in a bigger file, and then you get very good performance. So these are the kind of like very broad primitives or set of common primitives. Of course, the MPI standard is very big. There are all kinds of differences. We don't have time to talk into all those stuff, but these are the common features which most of the MPI users use. Any questions here?
Yeah, but about this collective I/O, that isn't it a feature of the file system?
No, actually, it's if you MPI 2 standard talks about the MPI I/O and then the collective I/O, like the Romeo.
I understand this, but the file system should care about this.
File system can provide some features. Distributed file systems, yeah, like a PBFS or something. Okay, I mean it stripes the data. That's what it says. But from MPI perspective, it doesn't say like how these different I/Os everybody is trying to write, how they will be represented to the parallel file system. That's what the collective I/O comes in play. Okay, the basic distributed file system provides mechanisms to stripe the data across the different disks. Okay, but it doesn't give semantics to the MPI layer. Okay, any other questions here? Okay, so with that kind of a background, now let's go into a little bit more into the design aspect of the MPI library. Okay, so if you take any network, for example, here I have provided like InfiniBand. If some of you are familiar, you will be hearing more in this workshop. So there are a lot of features, and similarly the MPI I talked over here, like the point-to-point communication, collective, one-sided, active, passive. So there is a lot of requirements. I call it like a demand side. This is supply side. Okay, and we need to bridge the gap. And this is where the MPI library comes into picture. And there are a lot of different design choices. Okay, like for example, the one-sided operation. How do I do it? Should I take atomic operations into account or not, or should I take RDMA operations account into not? So there are a lot of design choices, and finally you need to take the optimal design choices and then put it into the performance, scalability, fault tolerance, resiliency, power over stuff. So these are the kind of the goals when looking at the future systems. Okay, so any MPI library should be able to explore all these design choices and then put the best set of solutions there. Okay, and that's what we have been doing, especially at the OSU since the beginning of InfiniBand in 2001 when it came up. We had the first work on the MPI library called MVAPIC, which is MPI 1 standard. Then we moved to the MVAPIC 2, which is the MPI 2 standard. And since then, it has since 2002 supercomputing, it has been an open source software for the last 10 years. It has been steadily being used by a lot of people now, voluntary registration wise, who register at our site. We have more than 1,850 organizations in 65 countries. They can download directly from OSU site. This week, towards the end of this week, we will be crossing the 100,000 number. Almost we see every week like 1,000 or 1,500 downloads take place. It is also a part of all different kinds of stacks, the OFED stacks, different kinds of the Linux distros. And more importantly, it is also empowering many top 500 clusters. Although over the years, if you see every year like the top clusters use MVAPIC, MVAPIC 2 stack. We are also a partner in the upcoming NSF TAC Stampede system. Some of you might be already hearing about those in the supercomputing 2012. That is the target. This is from the TAC. It will be using the Intel mic architecture together with the Sandy Breeze kind of environment. So we'll be seeing. So this is a machine which will be a commodity cluster. Is trying to aim to cross 10 to 15 petaflops, and we'll see where it stands in another 6 months. So this provides a very high-level overview of the MVAPIC 2 stack. We provide a lot of different interfaces, something called a CS3. Then there is also Nemesis, all different kinds of PCI interfaces, all different kinds of platforms. And here we have for InfiniBand, iWarp, for Rocky. This is the QLogic, UDAPL, TCP/IP, even the shared memory model, which you can run on your laptop. And similarly also there is a Nemesis versions. The most commonly used is the left one. That is with the InfiniBand called Gen 2. That is the default, but you can actually change it to any of the other environments very easily to match with your network. So here, what I'll be talking in the remaining part of the talk, as I mentioned, take the car example again in mind. So within the MPI library, I want to go into some of the major components and discuss that what are these components, how they actually interact with the underlying system, in this case with the InfiniBand, and especially with multi-core platforms like the NUMA platforms. And tomorrow I'll be talking how it interacts with the GPU, like the NVIDIA GPU kind of things. And here I'll be talking how these designs have been done to focus on performance, scalability, fault tolerance, and provide some guidelines, especially as an user, if you want to deploy a very large cluster or if you want to even squeeze more performance from your applications, what aspect you should be looking for. Okay, and once again, I'll not be able to cover everything in 20 minutes. You can always take a look at the user guide. We have a user guide almost across more than 100 pages long, and it actually illustrates each and every component and how to tune those things. And please refer to that for more specific stuffs. And if you have already any questions, you can always ask us. We have a open MVAPIC discuss list. A lot of people ask questions, and we provide the feedback. Okay. So what I'll be talking here, just like the MPI standard, I'll be touching some of these issues like point-to-point, inter-node communication, how to get the best performance. Then I'll talk about intra-node communication, collective, one-sided, multi-rail, and especially scalability issues. When you go into a very large cluster, how do you reduce your memory footprint and get the best performance? Then how do you enable quality of service and 3D? Some of the systems, InfiniBand systems, are being deployed with the 3D torus, so how you can configure it for that, and then talk about some fault tolerance aspects. Okay. Now, typically within the MPI library, there are 2 different modes. One is called eager mode, which is to send short messages. Okay, and typically people have done that with send receives. We actually introduced a design almost 7-8 years back called RDMA first path. That means how do you use the InfiniBand RDMA to even to send this data with very lowest latency. Okay, and then there is a for large data. Typically these are buffered and these are unbuffered. So typically what you do is before you send the data, you do a start, and the receiver replies back saying yes, I am ready. Then you send the data and you do the finish. Okay, and here again there are different kinds of protocols we have. One is called rput, that means you can do RDMA write of InfiniBand, or RDMA read like rget, or we also have a fallback protocol called R3, which is send receive with packetized send. Okay. Now there are different trade-offs here, so I am just showing some few numbers here. So here you can see that this is for short messages, and if you use the RDMA first path design, that actually helps you to gain some performance compared to the basic send receive design. Okay, and here it's the next slide I'll show some different options, but the RDMA first path we saw for small messages you can get some benefits. But if you talk about let's say the eager protocol goes up to certain message size, and after that rendezvous, because the rendezvous has some overhead, whereas the eager protocol we are trying to copy and send. Okay, so as the message size increases, this copy overhead starts increasing. So this is what you can see, the blue line increases, and after in this platform, let's say after 16K, the rendezvous is doing better. Okay, and this is like a eager rendezvous is very common to any MPI stack. So the ideally what needs to happen is that for any platform, this eager threshold needs to be chosen properly. Okay, and we actually provide it as a parameter. The default is actually architecture dependent, but it can be modified by users to get smooth performance. So if you profile your applications and you see that, let's say your application is sitting somewhere here closer, let's say 17K. Okay, so might be adjusting this will give you some benefits. Okay, because depending on how much overlap you want to exploit in that applications, or if you want to push this a little bit higher or lower, all those things you can do to see what gives you the best performance. So here I am just going into some, I'll not go into line by line, but it shows how to actually activate. For example, here it says this is our default, which has the RDMA first path. There are 16 buffers for large and 32 for small. You can actually adjust this buffer. So here it says number of RDMA buffers is 32, so you can set up with more, but be aware that it will consume some more memory. Or you can totally disable RDMA first path also. Here it says for large messages, the default is rput, which is RDMA write, but you can change to rget, you can change to R3. So all these features we give, just like the car, if you remember, like the gear, so you can drive it and give the 1, 2, 3, depending on your slope. Okay, so similarly we give all these features because it is a distribution. We don't tune it for each and every platform. There are so many platforms, so many applications out there, but we give all these things. So you as the end user who is trying to deploy the cluster or who is trying to get the best performance for your applications, you can tune based on these features. Okay. Now with respect to, so that is the inter-node. Now the intra-node is actually gaining a lot of focus these days. Okay, especially if you see multi-cores are coming. I mean, so we have what the latest is 24, 32, 64 cores within the node. So actually a lot of communications now are happening within the node. Okay, so how do you really get the best performance? If you don't tune it properly, you will be losing time within the node, even though across the nodes you may win, but overall application wise you will not be getting the best performance. So here we have two kinds of mechanism. One is the standard shared memory, which copy from sender's user buffer to the shared buffer, and then copy from the shared buffer to the receiver's user buffer. So we call it like a 2 copy. So within the memory, like the sender writes and the receiver reads. And here again there is a eager versus rendezvous change you can do. The default is 16K, but you can actually vary it based on your frequent message sizes used in your application to get the best performance. But besides this 2 copy, several years back we introduced this kernel based module, okay, called Limit, and then we had a second generation of that called Limit 2. What it does is actually it eliminates one memory copy. So the idea here is that if a sender wants to send the data, what we do is by taking advantage of the kernel, we actually map the address of that buffer to the receiver, and then the receiver comes and copy the data directly from the sender buffer. So we eliminate one copy, and a lot of large deployments are actually using this, like SDSC, Trestles, Gordon, the Tax, Lone Star. So many places they actually trigger this to really get very good performance. And here there are some examples how you can actually turn on this Limit or the kernel module, and it actually shows the numbers. Now, on the shared memory side, we continuously optimize this design, and this is the very latest number we have with the MAPIS to 1.882 with Intel Westmere. We actually give you, like, using the standard shared memory, 190 nanoseconds, okay, from one core to the other core within the socket we can give you. Okay, no other MPI stack can come to this close the number. Okay, 190 nanoseconds, and then the intra-socket it's around 450 nanoseconds, and these are primarily used for the short messages. Now, for large messages, this is where the kernel module comes in, and here if you see, like this is the standard shared memory, and the green line you see the inter-socket. So the kernel module gives you very significant benefit. So if your message sizes are here like the 16K, 32K kind of things, you will really get a big boost. And the same thing happens also for bidirectional message bandwidth. Okay, so if your application has a lot of large data exchange, I'll really suggest you to turn this mode on, and you will very quickly see a lot of performance improvement for your application. Okay. Now the other thing which is becoming more important these days, with all these multi-cores are coming, these multi-cores, they are configured in all different manners, like inter-socket, intra-socket, and I'll show some example how they are connected with the network. So when you launch your jobs, you also need to make sure that they are running on the appropriate cores. Okay, so we call it like a core selection or core binding. Okay, so we have basically two flexibility. One is called bunch mapping versus scatter mapping. So bunch here, that means we have two sockets and we are running four processes. You can either put them like this, or you can distribute them over sockets. Okay, of course it depends on your application which process is talking to whom more frequently. And in the next release we are trying to actually provide some more selection schemes, and here actually shows some concrete numbers. So this is the latest Intel Westmere, 8 cores per node. Here you will see that core 1 to 2 for 0 byte exchange can actually do 170 nanoseconds here. This is a little bit better than the numbers. Yesterday only we took these numbers. This is some new release. We have done some little bit optimizations further. So here you will see like the same socket shared L3, so it delivers the best performance. On the other hand, if you have the cores 1 to 5 are talking, so this is inter-socket, so that is like 410 nanoseconds. So here you don't use the share L3. Okay, so even within this node, when you are assigning which process needs to run where, you need to be careful. Okay, if you have two processes which are talking more frequently, you should try to make sure that they follow this pattern, like they are within the same sockets, they are mapped. If they are mapped to separate sockets, even though like from a top level you don't see that, but it is actually incurring more communication at the bottom layer. Now, the same thing is happening on the NUMA. Like all the AMD platforms have all these issues, and many times people get confused. I mean, I show some numbers, you show some numbers, they don't match. Okay, so I'll illustrate why. So this is like a typical, let's say, Magni node, Magni platform. You'll see what happens is an animation. So let's say here the data is in this memory, so it goes like this to the network. Okay, whereas if the data is in this corner NUMA nodes 3 memory, so that will actually go over this hypertransport or QPI, then go there. Obviously, this communication will take more time than the data which is here. Okay, so that means that not only your processes, you need to within the node, you need to again map it properly, so that those which are trying to do more communication, they need to be assigned with the NUMA node 0, not here. Okay, and this you can do. Performance wise also you can see the difference, just like the standard voice latency. If you run it on different cores, so these are two nodes. This is core 1 to 1 versus core 6 to 6 or 12 to 12, 18 to 18. You will see performance difference. Okay, and Of course, the NUMA node 0, which is closest to the network card, always has the lowest latency. The NUMA node 3, which is the farthest, has the highest latency, and somewhere in between. Okay? So many times people present these numbers, even running the OSU latency, OSU bandwidth, but whenever you present some numbers or try to analyze it to make sure that which core to core you are taking the numbers, otherwise they will be a little bit misleading. Okay. Now let me quickly go to collective communication, and this is again, as I said, as the bigger and bigger systems are being deployed, this collective communication are becoming very important. How do we really tune it? How do we deliver the best performance? So within MIP2 stack, we have a lot of designs like multi-core aware designs. Then we take also intra-node communication and intra-node shared memory. I'll show some numbers in the next slide. But generally, this is the new design which we put almost like 6 to 7 years back. The idea is that just like the shared memory, we do better communication. We can take that into our collective. Okay? So let's say you are trying to do broadcast. As soon as one data copy comes or one data comes, we can put it in the shared memory and let everybody read from there. Okay? Which will be faster. So then for all collectives, we have a lot of like some default where we use the shared memory, where we use this 2-level, and these thresholds also you can adjust based on your applications. And I'll show some numbers here. And for example, this is on the TAC with 4,000 cores. This is the basic point-to-point versus this is the shared memory version. So similarly, all reduce. This is the basic versus this is shared memory. This is barrier. This is shared memory. So of course, in our stack, the shared memory mode is on by default, but you can also adjust it because after some SSIs, we see that there may not be performance gain, so we turn it off. But if your application has those kind of like message boundary, you should be able to adjust it again to get better benefits. Okay. Now the similar kind of things, one-sided issues are there. I talked about all these things. So here the design challenges are how do we have improved communication, reduce synchronization overlap, reduce synchronization and have some better overlap. Okay. And here it actually this illustrates the concept. So this is the y-axis is percentage overlap. This is message size. So if you are trying to do two-sided operation, even you use that I send ISC I talked earlier, you can get around like let's say 40% overlap. That means your computation with communication, you can get around 40% overlap. If you do like a one-sided or two-sided, so there is a way you can do the one-sided operation, but using two-sided, your overlap is almost 0. Okay, and that is actually a lot of MPI stack use. We have something called a one-sided over direct RDMA design, and here you can see that you can go into almost 99% overlap. Okay, and this is the same things we can also do within the node, not across the node. I mentioned earlier, like instead of this middle copy, we can eliminate the copy, and through Limit, we can actually go from source to destination. So that also allows the overlap to be enhanced. And this is the thing which the previous speaker indicated, the Gordon Bell finalist. We worked with the San Diego people and on TAC. So we took this AWP ODC application. They were written with the two-sided. Okay. Then we changed it to asynchronous two-sided because they were like using the blocking primitives, like I mentioned earlier, the MPI just send, MPI receive. We changed those to MPI I send, MPI I receive, while making sure that we are trying to exploit the overlap and not making any data corruption. And then finally, we changed that to the same program. We changed to use one-sided operations, and that's what we saw here. So this is like on the TAC. You can see on the 4,000 processes, like we are able to even squeeze. The blue line says compared to the original, we are able to get 11% benefits, and then here it's like 12% benefits. And so that's how the same application, same platform, but making changes to the MPI library and like using the newer primitives or the advanced primitives and rewriting the applications, we are able to push the performance. Okay, and this is just like a case studies. It can be done for any application. Okay, so if you have a critical application which is written in the old MPI send receive mode, you should be able to use the async operation versions like the I send I receives, and then the one-sided, you will be able to get this boost. Okay. Now let me talk a little bit about like a multi-rail. Okay, this is also becoming very important these days because now we have more number of cores. So let's say you have 32 cores or 64 cores. One network adapter may not be the best. Okay, it may choke. Okay, so some deployments are trying to come up with like two rails or 4 rails. In fact, there is a Tsukuba system in Japan. It has 4 rails. Okay, so now there are a lot of choices. If you think, so within the node I have 32 cores or 64 cores and I have 4 rails. So how do you try to utilize? So as a library designer, again we give a lot of flexibility. You can do binding. That means you can say, okay, process 0 just goes over rail 0. Process 1 goes to rail 1, and then you can do some round robin kind of thing. This is the binding. Or you can do some sharing, or you can do some striping. Of course, each one of these operations will lead to different kinds of performance, okay, based on your application, what you are trying to run. And here some numbers to stress that concept. So this is like a 2 Magni nodes connected with QDR adapters. Single rail versus dual rail. So you will see that you can push the unidirectional bandwidth, you can increase the message rate, you can also, using different policies, you get varied performance. Okay, so you need to find out for your application. Again, these are all runtime parameters, so it can change from application to application without rebuilding the MPI library. Okay, so as long as you know like what is your application communication pattern for your application, you should be able to use the appropriate mode and then try to get the best performance. Now let me talk a little bit about the scalability. And scalability is becoming a big concern as the clusters are becoming larger and larger. People want the best performance, and at the same time you also want the reduced memory footprint. Okay, because the MPI library internally uses a lot of buffers, a lot of internal stuff, but we don't want to grow it significantly as the cluster size increases. Then in that case you lose the memory which you can use actually for the applications. So here we have been monitoring very closely like what the Infiniment consortium has been doing. Like there was a shared receive queue was introduced earlier, so that instead of separate queue you use a single queue, and using the shared receive queue you can see that we are able to reduce the memory footprint significantly. We did this study almost in 2006. And same thing like UD and RC, you can also actually make some changes. There is unreliable datagram versus reliable connection, and we have done some studies, the trade-off, and there was an XRC which was introduced called extended RC, and that also we have it in the library. And finally what we have done is we have put all these things together as a hybrid mode, just like hybrid car, to give you the best balance between gas and electric. The same things we have done within the MPI library stack, it actually can move from UD/RC to the hybrid mode automatically to make sure that the hybrid always gives the best performance always. Okay, and this is application transparent, so you don't have to worry about it. Internally we have a lot of counters. We measure those things and we see who are communicating with whom, and there are different rules in which it can actually change. Okay, and this has been there in the MAPIs for many years. In the MAPIs 2 stack, since the last release we introduced it. So if you are running some application on very large scale system, I'll strongly suggest to turn on this mode, and you will see again very good performance. So let me very quickly touch the other 2 points. I know 2 minutes, so 2 more minutes. There is a QoS which is becoming important, and also the 3D torus. So there we have a lot of features. I don't want to go into details, but here again you will see that if you want to trigger with multiple VLs, you can actually turn on this mode to get very good performance, because within the switches you can actually utilize multiple VLs and the multiple buffers, so the contention in the network will reduce. And finally, just to touch fault tolerance, there is a lot of focus on the fault tolerance. We have proposed a lot of solutions over the last time. Let me just touch a little bit on the CR and migration. Especially on the checkpoint restart, we have again taken the advantage of like the shared memory concept. So we have an aggregation file system like called CRFS, and if you turn that on, you will see that you get almost significant benefit. So the blue line is the common one, and the green line is our new stuff. And we have done a lot of detailed study. You can see that through this, even to the file system, we are trying to reduce the accesses. We are trying to make it in a much more concentrated manner, and this is where we see the benefit. And then almost 2 years back, we introduced the process migration because that is becoming more important, not the checkpoint restart. So the idea here is that, let's say a node is about to fail. Okay, you can get a lot of sensor information like IPMI and all. Let's say temperature is rising, the disk is running slow, so that those are like the symptoms. And if you get those symptoms, you can actually migrate your MPI process to some other nodes so that you don't have to do even checkpoint restart. Okay, and that will actually reduce your, or rather it can increase your mean time between failures, and significantly it cuts down the time compared to a checkpoint restart. The migration has very little overhead, and also the data moved is minimal, and there again a bunch of parameters to tune this kind of stuff. Yes, Todd.
Are you doing the migration over InfiniBand verbs or over?
No, InfiniBand verbs. This InfiniBand verb. So as long as you define something like a spare node, okay, to where it can be migrated, you can do this. And this is within MPI natively, no virtualization, nothing. Okay, we have done those kind of solutions separately, but this is happening within the MPI stack. Okay, so with this, like, let me conclude. So here what I showed basically is like MPI is a dominant computing model. MapS2 is a popular stack, and just like again bringing the example of the car, just like the car designer does, within the MPI library we have provided a lot of different features, a lot of different modes, and most of these modes or the default settings are geared towards generic applications. Okay, but if you have a different user, if you have a different application, you actually need to adjust with the settings. Okay, and so as to squeeze more and more performance out here. And this is what I'll stop here, and tomorrow we'll go into some more advanced stuff like the collective offload, the PGAS, NVIDIA GPUs, and some of the MPI 3. And finally, the third day, I'll be talking a little bit in a different topic that is new to this conference this time. Even though we have worked on a lot of these MPI, all these techniques can be used for anything else. Okay, and since last 2 years, we have started looking at the Hadoop, Memcached, a lot of these enterprise applications, and I'll show you some initial numbers, how we can really redesign those stacks to reutilize the verbs level operations and then get the best performance. So with this, I'll close, and I know we are getting delayed for coffee. If you have any quick question, I can answer, otherwise I'll be here for the 3 days and I can interact with you. Thank you.